Okay, so we're going to have a think about the concept of momentum. Now, the idea of momentum in physics is quite close to its ordinary sense. Momentum is a measure of the hitting power, if you like, of an object. So consider two cases. Let's imagine a tennis ball, which is not particularly heavy, but travelling really, really quickly, okay, towards you, and you're over here, wondering what it's going to feel like if you're hit by this high velocity tennis ball. Okay. So this is an object with a small mass but a high velocity. Well, if it's got a really high velocity, you're going to feel it, so that's got quite a large momentum, probably. You're going to feel the impact. Now let's imagine a second case. Let's have not a tennis ball, but a truck travelling at low velocity. So now we've got a large mass travelling at a small velocity. So here comes our truck. Not travelling very fast, but maybe it's 10 tonnes in mass. Okay, and pretty obviously we're going to notice that if it hits us. So here we've got a large mass and small velocity, but we've still got a very large momentum. So you can see from our little examples that there are two ways, if you like, of building up momentum. You can build it up by having a big mass, even though you've got a small velocity, or you could have a big velocity even with a small mass. And if we multiply those two together, then we get a measure of momentum. Okay, so we can imagine a small mass object with a large velocity, that would have a lot of momentum, or we could imagine a large mass object with a small velocity, it would still have a lot of momentum. So multiply them together, that gives us a way of measuring the hitting power, if you like, the effect on impact of an object. Mass times velocity, momentum. Units, well, the units for mass are kilograms, the units for velocity are meters per second, and if you multiply those together, you get the units for momentum, which is slightly odd. They're kgm/s, kilograms meters per second. Notice that it's kilograms meters per second, not kilograms per meter second. Okay, so let's see what we can do with our idea of momentum. Well, one of the fundamental laws of our universe is the law of conservation of momentum. Conservation of momentum. This law tells us momentum remains constant. But that's a bit vague because obviously individual objects can gain and lose momentum. So what we really mean is that the total momentum of a system of objects remains constant. The total momentum. In other words, if you add up each of the individual bits of momentum of your interacting objects, whether that's billiard balls banging into each other on a billiard table, or asteroids colliding, or objects exploding, if you add up all the individual bits of momentum before the collision or the explosion, and if you add them up afterwards, you'll get the same amount. The total amount of momentum remains constant. Incidentally, that isn't always true. It's only true if there are no external forces acting. Imagine a billiard table that was sloping, then all the balls would start to roll, so the momentum of the body the momentum of the system of bodies would increase as they roll down the slope. So in this case, we've got an external force, the weight, the force of gravity, which is pulling the balls down the slope. Or if we took into account friction, then friction would dissipate the momentum of the balls on the surface as they move around. So again, we wouldn't have a conserved system. We wouldn't have a system in which the total momentum remains the same. But if we take away any outside forces, there are no outside forces, then momentum is conserved. The total momentum before any collision or explosion is equal to the total momentum after. And we're going to see how we can apply that law to analyse the motion of objects when they collide or during explosions. There's just one other point we need to notice about the idea of momentum. Momentum is a vector quantity, which means that it has size and direction. And typically in collisions we're thinking in one dimension, so we represent it using positive and negative values. And often we put positive going to the right and negative going to the left. And you'll see when we do some calculations why that's important. Okay, so that's the basic idea. Let's see what we can do with it. So one of the things that we can do with the idea of momentum is to analyse collisions and work out the velocity of the objects before or after. So I'm going to take a simple collision. I'm going to have a stationary car and I'm going to have a moving car, and let's suppose our stationary car, I'm just going to put an arrow there at 0 meters per second just to remind us that it's not really moving. I know it looks odd to call that 0 meters per second with an arrow making it look like it could be moving, but that's just a way of reminding us that it's not moving at all. Let's imagine that the car that's going to bang into it is travelling at, say, 10 meters per second. And let's imagine that they've both got a mass of 1,000, just to keep the sums simple. Now, lots of things could happen when they collide, but a simple case is where they get stuck together. So now effectively we've got one big car with a mass of 2,000, okay, which is going to be shunting forwards with an unknown velocity which we're going to call v. So here's our crumpled up, stuck together vehicles, the total mass of which is 2,000, and they're moving forward at an unknown velocity v. And the question is, how big is that velocity? So to work this out, we're going to apply the law of momentum conservation. The total momentum before the collision is equal to the total momentum after. So how much momentum have we got before the collision? Well, the car on the right had no momentum, it was stationary. The car on the left has got a mass of 1,000 and a velocity of 10. So that's the total momentum before the collision. After the collision, we've got a total mass of 2,000 and an unknown velocity which we've called v. So that's our total momentum after. So you can see how to solve this, I expect. We multiply on the left to get 10,000 equal to 2,000 times v. If I divide both sides of that equation by 2,000, I'll get a value for v. 10,000 over 2,000 is 5. So v, our unknown velocity, is 5 meters per second. Okay, so there we go. We've managed to work out the velocity of the combined object after the collision. It's going to be half the velocity of the original car. So that would be one fairly straightforward case where we could apply the law of conservation of momentum. Let's think of another type of example, and this time I'm going to imagine that motion in both directions happens. So I've got a cannon which is firing a cannonball, and the cannonball is going to fly out of the cannon with quite a high velocity. Let's give it a velocity of 20 meters per second, and let's assume that the cannonball has a mass of, say, 5 kilograms. And let's say that the cannon itself has got a mass of 25 kilograms. Okay, what's going to happen to the cannon as a result of this explosion when it fires the cannonball out of the front? Well, you can probably guess it's going to travel backwards with a velocity which we don't know, so we'll call it v. Well, how quickly is it going to recoil? Well, let's apply again the law of conservation of momentum. The total momentum before equals the total momentum after the collision or explosion, in this case the explosion. Well, how much momentum did we have before the thing exploded? The answer is none, 0. There was no momentum because the cannon was at rest and the ball was at rest. How much momentum have we got afterwards? Well, the ball is travelling at, it's got a mass of 5 and a velocity of 20, so we've got 5 times 20 for the cannonball, and we've got a mass of 25 multiplied by an unknown velocity v. 25 times v is going to be the momentum of the cannon. Okay, so let's see if I can solve that equation. So I'm going to expand out the bracket on the left. 5 times 20 is 100 plus 25 times v. Okay, now we've got to solve that. How are we going to solve that? Well, let's subtract 100 from both sides of the equation. So I'll have minus 100 on the left, and if I subtract 100 on the right, I'm just left with 25 times v. Now I can divide both sides by 25. 100 over 25 is 4, and there's a minus sign. So v will be equal to minus 4 meters per second. Okay, so what does the minus sign tell us? Well, the minus sign, if we go back to the question, you'll see that the velocity vector is pointing to the left, and as I explained, momentum and velocity are both vector quantities, so the positive direction indicates going to the right and negative velocity indicates that we've got motion to the left. So our equation has told us what we expected to find, which is that the cannon is going to travel backwards with a recoil velocity of 4 meters per second. So those are a couple of simple examples of problems that we can solve using the law of conservation of momentum.